In this video, we want to look at the third part of our Transformers lecture or video series. So we are looking at some objective questions that came on Transformers for WASSCE or WAEC candidates. So let's look at the first example we have over here. We have a transformer delivers a current of 10 amperes at 30 volts. If the primary coil of the transformer draws a current of 4 amperes from a 120 volt supply, we are to calculate the efficiency of the transformer. Now this is very easy and very straightforward. So let's look at the solution. Right, so if you're watching this video, I believe you've already watched either the first part or the second part of our transformer videos, and you've seen how we solve problems like this, and you've seen the formula and you know the formula, right? So here we have a transformer that delivers a current of 10 amperes at 30 voltage, right? So we were told that if the primary coil of the transformer draws a current, so it means the current in the primary coil, which is IP, is 4 amperes from a 120 voltage supply. So it means the voltage supply, which is EP, is a 120 volt, right? So it means the current given to us over here is the current in the secondary coil, which is 10 amperes, and then the voltage is the voltage in the secondary coil as well, which is 30 volt. So we have to calculate the efficiency of the transformer. Now to calculate the efficiency of a transformer, the efficiency is equal to power output over power input multiplied by 100, right? Now power output is equal to the product of the voltage in the secondary coil multiplied by the current in the secondary coil. So basically it is ES multiplied by IS, right? The voltage in the secondary coil multiplied by the current in the secondary coil, that's the power output, and then the power input is equal to the voltage in the primary multiplied by the current in the primary. So this is basically like ES IS over EP IP multiplied by 100, right? So this is equal to our ES is 30, so we have 30 multiplied by our IS is 10, then divided by our EP is 120 multiplied by our IP, which is 4, then all multiplied by 100. Are we okay? All right, so if you look at this, we have 30 multiplied by 10. Our efficiency is equal to 30 multiplied by 10 is 300, divided by 120 multiplied by 4 is 480, then multiplied by 100. So the efficiency is equal to 300 divided by 480, that will give us 0.625, then multiplied by 100, and then this will therefore give me 62.5% as the efficiency of this particular transformer. Okay, now here is a question based on the voltage, right? The primary voltage and then the secondary voltage, which kind of transformer are we dealing with? Okay, now if you say a step down transformer, you are correct, because the primary voltage is higher, the secondary voltage is lower. So it means you provided the transformer with a 120 voltage supply and you want it to reduce it to a 30 voltage supply. So this, okay, from a bigger to lower value is what we call the step down transformer. Okay, step down transformer, right? In as much as the voltage is reducing from 120 to 30, you can realize that the current inside is rather increasing, right? That is the relationship, right, between the voltage and then the current. They are inversely proportional when it comes to transformers. All right, so let's have a look at another question. So we have here the primary coil of a transformer has 3000 turns. If the transformer is required to give 20 voltage from a 240 voltage main supply, we have to calculate the number of turns of the secondary core. So this is the SSC 1999 question number 39. All right, so let's write down the solution to this problem. So we're told that the primary coil of a transformer has so the NP, the number of turns in primary, is 3000 turns. Okay, now if the transformer is required to give this 20 voltage from 240 main supply, it means our supplied voltage, which is EP, is 240 volts, and then our secondary voltage, which we are expecting, is 20 volts. Are we okay? So we have to calculate the number of turns in the secondary, so we have to calculate NS. That is what we do not know. Are we okay? So this is fairly easy, very easy. So for this particular question, the current or the voltage, the voltage in the secondary, the ratio of the voltage in the secondary to that of the primary is equal to the number of turns in the secondary over the number of turns in the primary. This is the ratio that we have. Are we okay? So if we make NS the subject over here, we are going to first of all we'll cross multiply. Are we okay? So this will give me my NS EP is equal to ES NP, right? So I divide both sides by EP, so this will cancel this. So the number of turns in the secondary is equal to my ES, right, which is 20 volts, multiplied by the number of turns in the primary, which is 3000, over the EMF in the primary, which is 240. Okay, so if I compute all of this into my calculator, okay, I'm going to get 250 turns, okay, as the number of turns in the secondary coil. Are we okay? All right, so this is the solution to this particular problem. All right, so let's have a look at another example. So over here we have the current in the secondary of a transformer, and the potential difference across it are 0.4 amperes and 240 volts respectively. We have to calculate the current in the primary if the potential difference across it is 20 volts. Remember that the efficiency of the transformer is 80%. Okay, actually this is the SSC 2001 question number 35. Question number 35. All right, objective question. Okay, then again, like I said, let's look at the solution to this problem. So let's first of all write down our parameters. They say the current in the secondary of a transformer and the potential difference across it is this and this. So it means the current in the secondary is 0.4 amperes, and then the voltage in the secondary ES is also equal to 240 volts. Are we okay? We have to calculate the current in the primary, so IP is unknown. If the potential difference, which is EP, is equal to 20 volts. Remember, we're given that the efficiency is equal to 80%, right? Now if I look at this, the voltage in the primary is 20, the voltage in the secondary is 240. It means that the transformer was supplied a lower voltage to produce a higher voltage, which is what we call a step-up transformer, right? All right, so let's look at the solution to this particular problem. Now if we are given efficiency, okay, is equal to power output over power input multiplied by 100, right? So if we want to get rid of the 100 over here, we divide both sides by 100, right, to get rid of the 100, or we can leave it like this. So basically it means that our efficiency is equal to the power output is ES IS over power input is EP IP multiplied by 100. Are we okay? Now this is the formula that we're going to use to solve our problem, right? So if I want this to use this as 80%, it means that this is already in percentage, so I can get rid of this over here, right? So I'll divide both sides by 100, both sides by 100. So this or by hand divide, so this will cancel this over here, and then we'll have this over here. So basically it means that my efficiency over 100 is equal to ES IS over EP IP, right? So my efficiency is 80, so it's 80 over 100. Are we okay? Either that, right? Or if you are confused over here, basically what it means that once you go to this formula, okay, in place of the efficiency over here, if you use 80, then you maintain the 100 over here. But if you want to use 80%, as in 80 divided by 100, then the 100 has to go away from here. Are we okay? That's basically why I am doing all these things, right? So 80 over 100, which is the 80% I'm using over here, so the 100 will no longer be here. So this is equal to the ES, which is 240, multiplied by the IS, which is 0.4, over the EP, which is 20, multiplied by IP. All right, so here I cross multiply. Okay, so I have 240 multiplied by 0.4 multiplied by 100 is equal to 20 multiplied by IP multiplied by 80. So to find my IP, so my IP will be equal to all of this divided by 20 multiplied by 80. 20 multiplied by 80, right? So this will get rid of this, this will get rid of this. So my IP is equal to 240 multiplied by 0.4 multiplied by 100, or divided by 20 multiplied by 80. Right, so my primary current, if I do my cancellation and everything over here, I'm going to get 6 amperes as my answer for the current over here. So the current over here is 6 amperes. So if you look at it, you realize that even though the primary voltage is low, okay, and then the primary current is high, the resulting current that is produced in the secondary coil is lower, but then the voltage is higher. That's a typical job of a step-up transformer, because the relationship between the voltage supplied and the current is inversely proportional. So EP is equal to 1 over IP. Okay, so this is the relationship between them. So thank you so much for watching. This is some WAEC past questions that came on transformers. There are more, but I think these 3 examples is enough for you to wrap your head around how to solve any problem that comes with transformers. So I'll combine the first lesson, the second lesson, and this particular one together in one to make one full video tutorial on transformers. If you need further assistance, you can drop a comment in the comment section below, or you reach out to us at mysciencetutorial@gmail.com. But don't forget to subscribe to the channel so you don't miss any video from us. Like the video, share with colleagues and friends.